guys, what's up? We're going to be starting here with the CCENT ICND1, or known as 100-105, the most current test for the date this video was made for the CCENT. Lecture in Lesson 13, Switch Operations in More Detail 2. So, I'm going to show you guys back. We're going to kind of go over a little bit in the last video, ARP. I'm going to show you guys kind of how it traces through. So without further ado, let's go ahead and move over to the monitor. We see we got packet tracer up. We got some switches, all switches. We got two PCs with some IP addresses, 10.1.1.1 and then 10.1.1.2 between these. But what I want to show you guys is how ARP works. So none of these switches have currently a MAC address table, and we're going to ping 10.1.1.2, which is the PC down here, and then we're going to get an idea of how this works because it's a simulator. So we're going to play it. We got a packet here. Going to play it. Notice it goes to switch 0, or the first switch, and then we're going to see it go down to the second switch down to here, direct path. Remember, it forwards out of all ports. Right there you can see, I'm going to stop it. You could see that it went to this one and this one. Notice how it comes to here. Once it hits this switch, it forwards out of all ports except the port that it was received on. So notice this. And then there we go. We go from port switch 3 to switch 2. Remember, forwarded out of all ports. And then it's going to go to PC1. Now watch. The message will be returned. There it goes to PC0. Now watch this. This is what happens when the MAC address table gets built. So PC1 or PC0 is going back to the path to respond. Now when it gets to switch 1, watch what happens here. Switch 1 knows where the packet came from because it has a MAC address table. So notice it only goes up to this switch and then to the PC for its return. And then the orange one's just, it does it 3 times. So let's do, if we do no constant delay, up, I did something totally different. That's STP, so we don't want to really go over that. Alright, but anyways, so basically we get a response, as you see, from there. So if we go over to, now that happens really fast. This is the real, and if we do a ping.1.1.2, watch how quick the responses come. That is happening very quickly over the switches. That's just a simulation, really slows it down, really shows you what's going on. So I'm going to set up the other one while we talk here a little bit. So, with that being said, STP is short for Spanning Tree Protocol. And you're going to see this has existed, this technology has existed for many years. And it serves a really important purpose, and there's a reason why it has not been replaced in today's terms. So, okay. So what we're going to do, we're going to have a simple topology here. We're going back over to the monitor here. As you can see, we got just switches. We got switches that are linked into basically what I would call a circle or a loop. So what does spanning trees actually do? We're going to explain what spanning tree does, and then I'll show you how it works, or give you an idea of what would happen if we didn't have spanning tree. So okay, everything kind of converges, but watch here. If I'm spread this out a little bit more, that way we can see it and zoom in a little bit more. So spanning tree obviously prevents basically switch loops. Because, for example, ARP would just, if you were forwarding packets out of every port as you received it, it would just keep forwarding. It would come over here, forward to here, forward. It would just be in a big loop, non-stop. Even if you had a PC, if I put a PC here, it would just be in a big, big loop. So what does spanning tree do? Spanning tree helps prevent that. But how? So if we go and look at this port here, we're going to come over here, we're going to take a look. Enable show spanning tree. what we're going to do, we're going to look at detail, or let's do summary over here. So you can see the word blocking. And as you notice, it works off of VLAN1 in this scenario. And we see we got one port that is actually blocking and one that is forwarding on this switch. Now the orange or amber color here, if you can see the dot, means that that is the port being blocked. So if we do, seeing if we can do show spanning tree VLAN1, you will notice the one that is amber, fast Ethernet 0/4 right here, is in a block status right here. BLK's for block. Notice that F0 or 0/1 for fast Ethernet is in a forwarded state. And we're going to get in more detail in the more advanced part of switches. This right now is just the function. We will get in a more broad detail in spanning tree. Right now we're talking about the basics of a switch, then we're going to talk about routers, and then you will get in a lot more advanced features that you may need to know for the CCENT. All my goal is CCENT is not to overcomplicate things. You just need to know what you need to know for the ICND1, and that's where I'm going to keep it at. So, I mean, yeah, I could go into a lot more detail here, but I feel for the ICND1, you don't need it at this point. Just understand that you have spanning tree, and it prevents not routing loops, but switching loops, basically. It prevents loops. And as you can see, there's blocking here. Let me go down here to this switch, and we're going to, so used to double clicking, and we'll do a show spanning tree. Let me first go into enable. Show spanning tree VLAN1. Notice that I'm in a forwarding, a forward status. Both of them are green. So I'm sending information through both ports, where this switch is only sending it through one port and this port is blocked. I'm just going to do this for justification to let you guys see. Notice I'm getting a root ID. Let's go over here, enable, show spanning tree VLAN1. This bridge is the root. Now what a root bridge in spanning tree forwards out of all ports. Always it will forward out of all ports unless you shut something down. So our root is elected, and it's based on, as we get into the more advanced part, I will show you how it's elected. But if we take, and let's actually compare what we got, switch 3, switch 1, switch 2. Trying to find the one that says it's the root, so it ain't that one. It's going to be that one behind it, switch 3. So we see that switch, I said it was the root. There's the cost. This is the root. Okay. So we have a cost here. Then we have a root. Notice that this cost is higher. It's 19 plus 19. So you can technically tell how many hops it takes from switch 1 to switch 3 by understanding spanning tree. And it knows where the root bridge is. But the root bridge will forward out of all ports. Let's take a look to see why this one may be chosen as the root bridge. And notice it gives us the MAC address of the root bridge on all of them. So all of them knows, is that one? Yeah. So they know the address or the MAC address to the root bridge. It shares it. But why? We'll go over right quickly why it's chosen. Why is it chosen as the root bridge? So let's take a look. All right, so this one is the root. Notice its MAC address matches this, and its priority matches the priority here. Now let's look over here. The priority is the same as the root bridge, but notice the MAC address is different. So if you remember from, and we'll hit this in a minute. So the MAC address is different, although the cost is the same. Let's go over here. The MAC address here is also different. So how does spanning tree know how to elect the root bridge? Well, when your priorities are the same, I can force the root bridge by changing the priority. The lowest priority is the root bridge. But if the priorities are the same as it is in these, as you see, all the priorities are the same, then it's determined by the MAC address. And the one with the lower value of the MAC address, and if you're not sure, you need to go back to hexadecimal, will be elected as the root bridge. And once you're elected to root bridge, you are designated to forwarding out of all ports. And notice that all ports have a cost assigned. 19, 19, 19, 38 for the cost. So we got, this one's a root bridge, so it has no cost. This is the root bridge. We have a 19, which is switch 3. We see switch 3, switch 3. Remember, the root bridge, if we can get this, is right here. So switch 3 goes through one port or one line, which makes it a cost of 19. Now if we look at the cost of 38 here on switch 1, we see 38. 19, one line is 19. The next line is another 19, so 19 plus 19 equals 38. If this port was sending out, it would also still be 19. So, now let's look at this switch, and I'll show you. It should be also 19. Enable, enable, show spanning tree VLAN 1. Notice it's forwarding, and the cost to the root bridge is 19. And notice, I will show you here. Let's switch 2. Let's get switch 4 up here, and I will show you that the MAC address, or switch 5 in this case. Look at the MAC address here. And this MAC address, sorry, wrong one. I was wondering. This MAC address is higher than this MAC address. So the lower MAC address is selected as the root bridge because the cost or the priorities are all the same. And let's say I want to change the priority. I want to change who my root bridge is on. Let's do, I'll tell you what, let's change it across. Let's change it over here. I want to change it on the one that, pick T. And what we're going to do is spanning tree, VLAN 1, priority, and we're going to set it to 4096, and then enter, and then end. Now let's see what happens here. Going to have a little bit of talking here. So on switch 2, we're going to do a show spanning tree VLAN 1. Notice now it's to the blocking, and notice that the cost is 38. So this was the root bridge. Remember, the root bridge forwards out of all ports. And just to prove this theory, notice that now it is blocking a port, and its cost is now 38 to the root bridge. And now I've changed. The reason it's higher, look at the priority of the root bridge to the priority of the remaining bridges. Notice it has a lower priority. So now I can force who becomes the root bridge if you choose to. And you can also change this for multiple VLANs also, which we will talk more about VLANs. But now let's do a show spanning tree VLAN 1. Notice now we're forwarding out of all ports. Remember, it was a cost of 38. Now we are at a root bridge, and our priority is the lowest in the group, which means that we as administrators made that become the root bridge. But notice, what I want you to know is in spanning tree, notice how it prevents routing or switching loops. I keep wanting to say routing. A line gets blocked from here. But let's get this even crazier. Let's say we got more connections. We're going to cross here. We're going to cross. And I just want to show you this so you get an idea of what. So now we got 2 more extra lines. And this can cause loops also. Let's give them a minute to converge. Remember, the root bridge should go green on its port. And I do not. I'm trying to get this to where you can see. I can see the middle one, but I want to be able to see the left one. There we go. Now you can see all the greens. Notice now they're green. Now look how the election's happening. Look where they're stopping. So this is blocked, and this is blocked. Now do you think the other one, I'm trying to look, and that one, the rest are on. So if you wish to draw this out, I can go here, I can go here, I can go, or no, I can't go here. So I can go here, I can go here, I can go here, I can go, nope, I can't go there. So if you look now, I've got the root bridge. Notice how the root bridge now is serving all the traffic. It is the main switch, and I will show you that it is going to forward on all ports. Show spanning tree VLAN 1. Remember, it resides on VLAN 1 for default. If I make a VLAN 2, it would also reside on VLAN 2, so you can make multiple instances of spanning tree can run based on your number of VLANs. And there is different types of spanning tree also, in which we will talk about here in a second. So notice it is forwarding out of all ports. We go over here, show spanning tree VLAN 1. Notice it's blocking, and then forwarding. Now when it says alternate, if this port goes down, let's turn off fast Ethernet 01. Let's say the port goes down. One of these ports here will come up. Alternate means backup, basically. So let's go into the switch. We're going to go config T, interface, fast Ethernet. This is Ethernet up 03. We're going to shut down. We're going to shut down that port. Now this port's going to go down. Oh, nope, we hit the wrong one. Sorry, guys. I see now it's the middle one. My bad. So we're going to do a no shut on that one. And we're going to go back to interface. It's actually fast Ethernet 01, it looks like. Shut down. So notice this shuts down. This shuts down. Now this is administratively down, so this port will be down, but if it comes up, it will forward. Now we should see something on this switch start to come up. It's going to say, hey, this is down. We need an alternate path to get to the switch. So let's see what happens here on switch 5. It's communicating. It'll continue to send spanning tree or accept spanning tree on this. It would take it a minute to converge. Let's see if we can show or show spanning tree VLAN 1. Now we have, notice this port is opened up. Now what happens if I turn back on interface fast Ethernet 01? What happens if I turn this back on and no shutdown? It's going to come back amber. Now let me show you and show spanning tree VLAN 1. Notice we're at a listening state, and we're about to talk about that. So listening. Notice it says route, meaning that it is a path to the root bridge. Now it's in a learning state. So it went from a listening to a learning state. And now we're green, so now it should be forwarding. Forwarding means it's active and ready. Notice it says route. We'll go over here to the VLAN 1. Notice we got a route. Now see that we have a route, and look, now we have a designated. Both of these are forwarding. So what's the difference between route and designated? A route is going to the root bridge. It's the line or port that goes to the root bridge. Designated is one that does not go to the root bridge, but it's online or open. In this case, this one's open. even though it's not going to get to switch 5, it remains open. And the same thing, these are all forwarding, although we've got some blocking here. Now you could say, if it's blocking traffic, how does it know to be a backup route? Remember, it's not actually blocking the spanning tree traffic. It is only blocking all other traffic. That is how it negotiates to determine what ports need to be up or blocking and what ports need to be forwarding. So that is basically how your spanning tree works. It stops loops, for example. So what I'm going to do now is we're going to go over here. I'm going to pull up something for you guys. So let me get you. So spanning tree has different technologies, but we're going to talk about the basically very start of how it kind of works and the statuses that it goes through. So it goes through different statuses. So let's get up here. I'm going to try to pull up the Cisco website. Here we go. Let me see. I'm going to try to increase this view if I can. There we go. I'm going to just root in. There we go. Go one more. Here we go. Okay, guys, let's go back over to the monitor. So I'm right here, and this is straight off the Cisco website, and this is over spanning tree, as you can see, STP. So we have state of ports, and you will need to know this and how they actually work. So you have disabled. This port is disabled. It will not transmit or receive any traffic. Also, will not accept any STP traffic, usually also. Then we have the blocking, which we talked about. This port is enabled, but blocked by STP. So it doesn't mean the port is down. It means that it's blocking state. It means it's preventing switching loops. And if you have switching loops, you're going to have a broadcast storm going on. That's the whole reason for STP, is to stop broadcast storms. And it will shut your network down very quickly, or it will be really slow before it shuts down. It will not transmit or receive any traffic except STP traffic. But in this reference, they're talking about basically network traffic. So the listening state, so it goes from blocking to listening to learning to forwarding, and you will need to know that order and what it does. It goes from blocking to listening to learning to forwarding, and you will see something similar to that, or you will need to know this for your ICND1. So alright, moving on to the listening state. This port will receive the process STP bridge protocol data units, so BPDUs, but will not forward any data traffic. So basically, when you're listening, you're basically only talking to or with STP bridge protocol. That is it. So no traffic in the listening can go through the switch or through that port. So even though blocking, also in the listening, you are not transferring any data through the ports. You're only talking to STP bridge protocol. Then we have the learning state. This port will start to learn MAC addresses from the received packets. It will also receive and process STP BDUs, but will not forward any data traffic. Once again, does not forward any data traffic. So blocking, listening, and learning still will not do any traffic push through the ports. We're talking to STP and listening. Basically, we're talking to STP. We're determining how STP's going across everything. Listening, we're learning MAC addresses from the received packets, but we're still not transferring data across ports. And receiving, we're still receiving and processing STP BPDUs. And then last but not least, forwarding. This port is forwarding data traffic, processing PBDUs, or BPDUs, sorry, and learning MAC address, which means building a MAC address table, still taking in STP traffic, and we're forwarding all data network traffic. So blocking, we're only talking to STP. Listening, we're also talking, or still listening to STP, but now we're, blocking is port is enabled but blocked by STP, will not transmit or receive any traffic. Listening, this port will receive and process STP bridge protocol data units, BPDUs. BPDUs is short for bridge protocol data units. So we're talking to STP, but we're not forwarding there any traffic. And learning, we're building a MAC address table and still talking to STP. And forwarding, now we're moving traffic across the ports. The switch is actually operating as a switch for the network or the data. Now, if you really want to focus, if you can't memorize all of this for the ICND1, I highly recommend you understand that traffic is not being transmitted by blocking, listening, learning. It only transmits when you go to forwarding. Now, this can take anywhere from 45 seconds to a minute in your earlier protocols for STP or your earlier technologies of STP to get to forwarding. They do have what they call rapid, which is much faster than this. I mean, it goes up very quick from here. So we also got the port roles here. We're going to look port roles. We have the root port, the port with the lowest path cost to the root bridge, so it's going to be connected to the root bridge. Designated port, which we've seen, the port with the lowest path cost on a LAN segment. The LAN segment will use the designated port to reach the root bridge. And then we got blocked port. The port that is neither a root port nor a designated port. It is a blocking port. And then we can see here we done went over this, and we'll look at the bridges right quick. So, or the root bridge, and this is the stuff that they show you. Got cost, and more of this will be over there. But check the STP status in this VLAN. So STP runs across VLANs and ensures a leak-free topology for any bridged LAN, which is switches nowadays. But they used the term bridge, and the reason why is bridges it was bridges, then hubs, and then came switches. You'll not see bridges in any network probably today. I don't know if I've ever seen a bridge. I've seen hubs, and I remember when hubs were being used, but now bridges I have not really seen. I might have seen one physically, but never seen one actually connected. And now switches is your most common connection. So guys, that is how STP works. You will need to know that for your ICND1. And remember, it is to prevent loops. It creates a loop-free environment between switches. And you will need to know how it operates, what a blocking port is, the listening, learning, and forwarding, and know how it basically picks a root bridge. And remember, it's based on priority. We can force a root bridge, so the lowest priority becomes the loop bridge. If that is a tie, then it bases it on the MAC address. So your MAC address will be the next thing. So I'm going to put this over. I'll show you guys right quick. So we're going to go back over to it and look at, I'm going to go to this one. Spanning tree, VLAN 1. So notice that it goes first by the priority address on the root bridge. And, I meant not the priority address, the priority number. The lower, basically the lower, it will be the root bridge. The higher, it will not be the root bridge. So if you have the lowest priority, you become the root bridge. And if it's a tie on your priority, then it bases it off the MAC address. And once again, it's got to be the lowest MAC address in the table. So if your priorities are all the same, or your priorities the same, or you even have two with the same priority, next it will do the election based on the address or the MAC address. Now your hello timers and your max age timers, this is how STP picks up. You won't really have to know this. I don't think they'll say, I did not see anything even close to this on the ICND1. But if you need to know, it's a hello timer or hello times every 2 seconds. STP is sending out, talking to the switches, and the max age timer is 20 seconds. That's the max age before it drops the switch to determine it ain't basically there anymore if it doesn't get a response back from the hello. And then a forwarding delay is 15 seconds. What has to do with STP? That's your forwarding delay from there. And you notice we still got the same thing up here. It shows us for the root bridge. Here, these are by default, and for the ICND1, you will not have to really understand these values to the max, but you will learn about them in the router, and it will basically cover for this also. It's the same concept. So guys, that does it for this video. I hope that this video has been of benefit and helped you understand how STP works in a switch environment. If you enjoyed the video, please subscribe to the YouTube channel and like if you prefer. If you have any questions, please feel free to comment or PM me. And until next time, guys, see you in the next video, which will be lecture and lesson 14. And I will go ahead and tell you it will be over collision domains. See you guys next time. Peace.